All right, so today we're going to take a look at section 4.3, which is Riemann sums and definite integrals. Last time we looked at these left and right rectangles, right? And we talked about the fact that if we increased our number of rectangles, we would increase the accuracy of our estimation, and talked about if somehow we could let those rectangles become infinitely dense, right? Like infinitely many in the space that we have, we might actually get the right answer or something super close enough that we're okay with it. So that's actually the idea of a Riemann sum. So there's a lot of language here. Go ahead and fill in your two blank spots if you would, and then I will read and we'll talk through the definition. So blank spots are here and here. All right, so we're going to take a function, and it's going to have a closed interval, right, a starting point and an ending point. And we're going to let delta be a partition of the interval. So it just means like when we subdivided all of our intervals before, right? Delta x is just what we had and we called them. So it starts at A, it ends in B, and we have all of these, sort of subscripted x values in between, n of them in particular. And delta x sub I is the width of each of them. Okay, so whatever interval you're looking at. The reality is that those interval widths, we did it in such a way that made it easy to calculate by making them equal. They don't even have to be equal for this process to work, which is kind of cool. If C sub I is a point on the interval, so we used the left-hand endpoint, the right-hand endpoint, the midpoint, right? But this is actually telling you can use any point on the interval, and it will work. So if you take that and you take the multiplication, or the product rather, of the function height and the width, and you multiply them, right? That gives you an area, agreed? And then you add all those areas together, right? That's what this notation means, is adding all of those areas together. That if you do that, then this is actually called a Riemann sum for the particular partition delta. So the sums that we saw in section 4.2 that we talked about last time are examples of Riemann sums. But as I've described today about how we can vary the width and we can use any point as the height and so forth, we get a more generalized description, more general Riemann sums as well. So that was one of our, so we had two things in our title, right? Riemann sums, I've defined for you what they are, and then definite integrals. So this is our other definition. And again, there's like several places for you to fill in, and then I'll read it. So let's see if I can underline them. Integrable, oops. Definite integral, lower limit of integration, and upper limit of integration. Those are the places where you should fill in on your notes. So this definition kind of picks up where the last one left off. Still have that closed interval A to B. We have this limit of the Riemann sums. We have a partition delta. We have all those kinds of things. The part that's different is the word limit that I just said. Right here at the beginning, it does something very interesting. It adds a limit. You guys thought we were done with limits, didn't you? We came back up for the quiz today, right? From the material we did. Or not the quiz today, from the test today that we went over. And it's coming back up again here. What this is telling you is that partition, the widths of your rectangles are decreasing and they're approaching zero. They're becoming infinitely small. So the widths are practically nothing left, right? But we're still multiplying by that width and that random C value in the interval, right? And we're adding them together. That process is still happening. Our widths are just getting infinitely small. Infinitely small widths mean infinitely large numbers of rectangles. Those go hand in hand. So when we do that and we take that limit and we let those widths go to 0, we actually see this notation pop up. Now you've seen that script S before. That's not new. You've seen the delta, the dx at the end, also not new. What's new is the a and the b, right? You didn't see that before. We didn't have that before. And that a and the b are in fact the upper and lower part of the interval that we defined at the beginning. It's this a to b here. So interestingly enough, what this is actually saying is that there is a relationship between this integral process, these antiderivatives you've been working on that you're going to take a quiz on Thursday, and this summation of rectangles process. And the relationship is that if we take these rectangles and we let them get infinitely small, we can actually find that value instead of finding infinitely many rectangles by using an antiderivative. The limit is called the definite integral of f from a to b. The number a is called the lower limit of integration, and the number b is called the upper limit of integration. All right, so some of you who have had some calculus before want to jump to where I was wanting to jump to as well. Don't jump with me just yet. Hold tight, okay? A few more things to show you. We've talked about continuity in different places. We're going to talk about it again. If we have a function that's continuous, then it's integrable. It doesn't work the other direction. Just because it's integrable does not make it continuous, okay? But if it's continuous, you can find these areas, okay? So this definite integral from a to b of f of x dx will in fact exist. If f is continuous and non-negative, that's another condition that didn't exist on the last slide, right? Non-negative, that is, we are completely above the x-axis, on the closed interval from a to b, then the area of the region is exactly what we've been describing. So as I've described this, and as you drew pictures in the last section, hopefully you drew some pictures, right, of these areas, we sort of fudged things a little bit. Everything we worked with was already above the x-axis, right? It was. And we kind of didn't talk about, well, what happens if it's below the x-axis? So just recognize the fact that everything we've been working with has had this extra condition sort of on it of being non-negative that we haven't really addressed until now. All right, so we're going to take a look at some examples. I don't even know if this is the same problem number anymore because this was an old textbook that I used it from. It says to set up a definite integral that yields the area of the region and do not evaluate. So what I would like to show you is what the function is. It had a picture in there, and I'll draw it here too. So the function, if it's the same on there, is f of x equals x squared. You know what that equation looks like. And the shaded interval is actually like this. So I'm just going to draw this in. This is at 0 or 1 and 2, 2 and 4. There's 1. It's not to scale very well, but imagine that it is. And this is shaded in. Okay, so don't do more work than you're asked for. That's always a good plan, right? Raleigh's theorem, it showed up on your test that we just looked at. Some of you did more work than you were asked for. All this asks you to do is to set it up. Doesn't ask you to find the area. Just set it up. So what it's wanting you to do is to take a look at this new notation that you now have, and it's wanting you to create what the notation should look like for this problem. That's all it's asking you for. So notice what you have to have. You start with the script S, and you start with the A and the B interval on there, right? So looking at this diagram, here's my script S. What is my interval? What are my lower limits and upper limits of integration? 0 and 2, exactly. So the picture tells you what to do. The next thing that I'm supposed to have is I'm supposed to have the function itself. What is the function that I'm dealing with here? X squared. And then dx at the end because it's with respect to the variable x. If we had a function and it was t squared, we would put dt at the end. Okay? That's all this question asks for. It's a really easy question actually, right? Very short, not asking for much more or anything more. Okay, the other thing that we're going to take a look at next has to do with what happens when we have equations that have other ways of finding area. So we've approximated things in the last section with lots of rectangles, and that's great. But sometimes rectangles and other shapes can actually be used to find exactly the area that we're looking at. We couldn't do this problem. We couldn't actually find this area with the techniques I'm going to show you next, okay? Because it's a curve. That's really why. Y equals x squared is a curve. But this equation is not a curve. So here is a function here, right? This function is 4. What in the world does the graph of f of x or y equals 4 look like? Yeah, exactly. Okay, Parker and Eric were drawing it in the back for me back there. Whoops. It is a horizontal line. At height? 4, yeah. I'll draw it red. So here's my horizontal line at height 4. So this is y equals, or f of x equals 4. And where does it say that I'm supposed to start and stop my interval? Yeah, start at 0, stop at 3. So 0 is on the y-axis, and 1, 2, 3 is right here. So the area that I'm looking at is from here to here, and it's shading again down to the x-axis. So this is my area, right? And the cool thing on this section when it asks you about using a geometric formula is it's always going to be a shape that you know an equation for, or you should be able to find an equation for very quickly if you've forgotten it. What is the shape? It's a what? It's a rectangle. You bet. It's a rectangle. And you know how to find the area. This is one rectangle, right? We've been doing lots of rectangles in the last section. What's the area of a rectangle? Yeah, length times width. So what are the length and the width of this particular rectangle? 3 and 4, in whichever order you like. So the area here is 12. And I don't need any calculus. The calculus came with interpreting the original statement and what it meant in terms of a graph. After that, you're using arithmetic, actually, to find it. How about this equation? So again, the equation is 3x plus 4. What is that an equation of? It is a line, you bet. Can you tell me a little bit about the line? What do I need to know in order to draw this line? Has a y-intercept of 4, and a slope of 3. And I'm supposed to be going from 0 to 2, right? I don't have to go out very far. So I'm going to put here 2, and we'll just plot some points. So if I plug in 0, or if I look at the intercept, the y-intercept, it's 4, right here. And then if I plug in 2, what do I get? 10. So over here at 2, I need to be up at 10. That worked out nicely. And it's a line. I know it continues beyond that, but I'm just going to draw that portion of it, so just that line segment, since I know I'm starting and stopping there. And I'm looking at, this is not drawn very straight down, pretend for me for a moment, this area. All right, does anybody know what that shape is? It is a trapezoid. That might not be a formula that you remember very well, and it's actually okay if you don't. If you do and you want to use a trapezoid formula, I'll show you that in a minute. But if you don't recognize this, could you break it down into two different shapes that you do know formulas for? A rectangle and a triangle. So I'd like to do that perspective first because it's so nice. If you break it right here into pieces, you have a rectangle and a triangle. And I know you know the area formulas for those because we use them so frequently when we're in earlier grades. So this shape right here is my rectangle, right? So how would I find, or what is the area of that shape? It's 8. It's 4 times 2 for 8. All right, my shape above, I'll highlight it in blue. What's the formula, because we haven't written it down yet, of a triangle, area formula for a triangle? Right. So base times height divided by 2, or 1/2 base times height, some version of that. What's the base? What's the height of this? Yep, 2 is the base, if you think the bottom part of it, and then the height would be 6, because it starts at 4 here, and it extends up to 10. That's 6 tall on the blue. So what is the sum, or the product rather, if I multiply these together? It's 6, and then I need the sum of these two, which would give me 14, right? Okay, if you wanted to do it as a trapezoid, does anybody remember the area of a trapezoid?
Base plus base divided by 2 multiplied by.
Okay, so base 1 plus base 2 divided by 2, it's averaging the bases, the unequal sides that are parallel, times the height. Okay, so in this picture, let me draw the image in here. We'll use the dark blue. Oh. This piece and this piece are the parallel sides, so those are my bases. Okay? So one base is 4, and the other base is actually 10, right? The full length, divide by 2. And then the height would be the distance between my bases, right here. And the height then on this one would be 2. So if you, this one actually works out really friendly because the 2's will cancel, but I end up with 4 plus the 10 for 14. They don't always simplify quite that simply, but same evaluation, right? Same value at the end. All right, a few more things to finish this up. This is what happens when we look at intervals from different perspectives. So these are 2 special definite integrals. If you take the interval where it starts and it stops at the same value, you get an area of 0. And that should be no surprise. There's no width. The width is times 0. Think about an equation of a rectangle, right? Length times width, width 0, there's no area. If you look at the interval from A to B and B to A and you reverse the order, it makes it negative. Okay, you switch the order and it actually changes the sign. If you take an interval and you break it into pieces, you could add the first piece's area to the second piece's area, kind of like we did with our triangle and rectangle. We didn't break it horizontal, or we didn't break it along the x-axis, we broke it along the y-axis. But if you break it into pieces, it's okay. So this is saying, imagine you have this, here's A, here's B, and C is somewhere in between. If for some reason it's easier to find this piece and this piece separately, you're still going to have the area of all of it. Seems reasonable, right? We can break it into pieces. Okay, and the last properties that we're going to look at today, talk about things that we've seen before in different contexts. We've done this for limits, we've done this for derivatives. If there's a constant being multiplied, it doesn't affect things any differently than if you multiply it after you've done the antiderivative. We saw that in one of our rules when we did the antiderivatives back on section 4.1. It's called the multiplier rule. It works for definite integrals. And the same is true for sums and differences. If I have the sum and difference of two different functions, I could find them each separately and then add those results together, and it would be the same. Okay, so it's all the same things that we've seen happen before, happening again for definite integrals instead of just for antiderivatives when we saw them before. Okay, so on 4 and 5, again, I'm asking those of you who have seen pieces of this before to hold your horses. This is not asking you to take antiderivatives with antiderivative rules. Okay? What it's asking you to do is apply the theorems that we just established. For instance, on number 4, you notice there are 3 functions adding and subtracting together, correct? So according to the example number, or not example, but the theorem that we just did, theorem 4.7, property number 2, I should be able to separate them into 3 separate functions, or definite integrals. So that's what it's asking me to do. It's asking me to rewrite this with each piece separate. Okay, is everybody good with that so far? That's the second part of the last theorem that we did. And then it's asking me to take a look that some of these I know the value for, right? This tells me that that first piece that I have, the integral from 2 to 4 of x cubed dx is equal to 60. I don't have to do anything. I'm told that it's 60 and I don't need to go any further. Yes, Eric? Oh, you already did. I just wrote it down wrong. Thank you. Good fix. Okay, so this piece is 60. It matches exactly. The piece in the middle does not exactly match this. What's different about it? It's got that 3 in front, right? But the other theorem, part 1 of this previous theorem, said that I can pull the 3 out, yes? So I'm going to take one more step to show that I've done that. I'm going to pull my 3 out, 2 to 4 of x dx. And then, here in the next step, I will be able to say that this piece I know the value of. It is 6. So here I've got negative 3 times 6. Okay, this one always catches people off guard. Any idea what's living inside here? It's a 1. There is a 1 living inside there. But my problem doesn't have a 1, it has an 8, right? Okay, but the 8 is the same as 8 times 1, right? So just like I pulled my 3 out from the 3 times x, I can pull my 8 out from the 8 times 1. It almost feels like we're doing just a little bit of silliness. I understand that. But definitions are what we're working on in this particular lesson. This is what I have.
It's a plus.
It is a plus. I changed it earlier. Thank you. So here I have plus 8, and then the sum is, or the definite integrals value is 2 on that one, according to this, right? So I really have 60 minus 3 times 6 plus 8 times 2 for a grand total of what? What is it? 26. I have something different. 58. That is what I have, actually. Probably the right one, 58. Okay, so I know you're doing WebAssign where you could probably jump from here to here and not show me anything, but when you get to your quizzes and tests, you're going to show me all those steps, right? Correct, absolutely, because that's what it means to use the definitions, which is what it's asking for in this problem. One more question and we're going to be done. You ready? Okay, same premise, same evaluation pieces at the front, right? The definite integral values. What do you notice is different about this problem than the last one? Very different. They're flipped, right? The 2 and the 4's locations are different. So I need to switch them back into something that matches what I have. They need to say 2 to 4, not 4 to 2. But I can't just change them willy-nilly. What do I have to do if I've switched the order? You put a negative sign in front. It's going to change positives to negatives, negatives to positives. So as I look at this now, I have a negative from 2 to 4 of x dx. And then this negative here with this negative here will make it a positive integral from 2 to 4 of 7 dx. But just like we had on the 8 at the end of this one, what do I have to do with the 7? Pull it out. So I'm going to do that right now so that I don't have to do an extra step. Wonders of technology, just allow me to move things around. Every now and then on paper I try to do something and I'm like, oh man, such a bummer. Okay, the negative at the beginning, but then what is the definite integral from 2 to 4 of x dx? It's 6 plus my 7, and what is the definite integral from 2 to 4 of dx? It's 2. Negative 6 plus 7 times 2 would be, it's 8, yeah. It's 8. Any questions on that? All right.